Welcome to session 5, unit 5 of our financial modeling course. In this session, we are going to consider the estimation and other selection of our financial time series models. By the end of this session, we should be able to assemble a set of candidate models for our time series model, and also we should be able to explain the concept of information criteria as it is used in fitting the best model. Estimation or order selection. One challenge in doing time series analysis is simply estimating how many lags or past observation to include in our equation. In other words, it simply speaks about how far into the past an observation is relevant, or we can't predict an observation. This simply requires a greater skills and experience, but there are also no hard and fast rule for this determination. Sometimes we have to depend on a try and error experimentation in order to achieve this model or this model estimation or selection of models. The number of parameters that we have to consider in this estimation, that is the number of lags for our moving average, which is the Q, and the number of order or the number of lags for our autoregressive model, which is the P, and the D refers to the number of times we have to difference the data series in order to achieve stationarity. Once the order is determined, we have to rely on the maximum likelihood estimate. So one will ask what is the maximum likelihood estimate. In statistics, the maximum likelihood estimate is a method of estimating the parameters of an assumed probability distribution given some observed data. This is achieved by maximizing a likelihood function. So under the assumed statistical model, the observed data is the most probable data set. The point in the parameter space that maximizes the likelihood function is what we call the maximum likelihood estimate. Under the maximum likelihood estimate, we find the value of the regression coefficient, which maximizes the probability of obtaining the data that we have observed. The maximum likelihood estimate is similar to the ordinary least squares that we came across in our earlier sessions, where the regression coefficient were obtained by minimizing the sum of squared errors, as we have shown in this simple equation. This is the squared of the errors, and this is the sum of it. So this is error term, and this is the sum of the error term, so the squared error term. Information criterion. Mostly we come across the information criterion, which is simply a hasher or a penalty that is being given for adding more parameters in our model estimation. So one will ask, what is information criterion? Information criterion is a measure of the quality of statistical model. It takes into account how well the model fits the data and the complexity of the model. Information criterion are simply used to compare alternative models fitted to the same dataset. All things being equal, a model with a low information criterion is superior to a model with a higher information criterion. So you could clearly see in our equation that the information criterion, which in our case we are considering the Akaike information criterion, the Akaike information criterion is given in this equation. So with the Akaike information criterion as one of the most important information criteria that is being used to assess how a model fits the data set, is being defined as a mathematical method for evaluating how well a model fits the data it was generated from. In statistics, the Akaike information criterion is used to compare different possible models and determine which one best fits for the data. The AIC, or the Akaike information criterion, is calculated from a number of independent variables, which is used in building the models or the maximum likelihood estimate of the model. So we define our Akaike information criterion using this equation. So in this equation, we have there are parameters in this equation. We have our L, which is the likelihood of the data given the parameters, and the K function. This K is simply supposed to be equal to 1 if and only the alpha component is equal to 0, and it will also be equal to 0 if the alpha component is equal to 0. Note that the last term in the bracket, this term represent the number of regression coefficient, that is the P represent the AR model, the Q represent the moving average model, and the moving average model. For our Riemann models, mostly we prefer the use of the corrected Akaike information criterion, which is given in this equation. So this is the corrected Akaike information criterion. But the Akaike information criterion is also not the only information criterion that is used in determining or in diagnosing or in assessing the fitted model. We also have the Bayesian information criterion. The Bayesian information criterion in statistics is a criterion for model selection among a finite set of models. Mostly models with lower Bayesian information criterion are generally preferred. When fitting a model, it is possible to increase the likelihood by adding parameters, but doing so may also result in the overfitting of the model. Both the Bayesian information criterion attempt to resolve this problem by introducing a penalty term for the number of parameters in the model. The penalty term is mostly harsh. The reason why we prefer the Bayesian information criterion is that the penalty term in the Bayesian information criterion is harsher compared to that of the archaic information criterion. So the Bayesian is also conservative, and it selects too few lags in modeling, and the model that provides the best fit to the data is the one that is selected in the Bayesian information criterion. In assessing your model using the information criterion, you have to choose the least information criterion, that is the AIC, AICC, or the BIC. The one with the least model, or the least value should be selected. In this session, we have assembled a set of candidate models for our time series, and we have further explained the concept of information criterion as a base to select the model that best fits the dataset. We continue with the next session.